who did his PhD from AHEP with Professor Shambhi Trivedi, and currently he's a postdoctoral fellow in ICTP. And today he shall be speaking on self-similar gravitational dynamics, singularities, and criticality in two dimensions. His hometown is in Calcutta, so he's currently visiting his hometown, and he will be leaving again very soon to ICTP. So it's all yours now.
Thank you very much, and thanks especially for making this possible. And I'd like to thank everyone for showing up here at this hour in the morning. So, and it's a pleasure to be back here at SMBOS. I remember a few years ago I had come here for interview after my MSc, and it's really great to be back here in a different capacity this time. So I'm going to talk about, as Shunananda said, about self-similar gravitational dynamics, singularities, and criticality in 1+1 space-time dimensions. So before I describe my work in detail, let me try to spend a few minutes describing why I want to explore the problem that I am exploring. So the reason goes back nearly, actually exactly 30 years back, when one of the most surprising results in general relativity was discovered by means of numerical relativity, and it came as a complete surprise to everyone. And this phenomenon goes by the name of Chopwick scaling, named after its discoverer, Matthew Chopwick. The phenomenon is as follows. Okay, thanks. So this problem considers spherically symmetric massless scalar field collapse in 3+1 dimensions, and one can specify some initial value data of this massless scalar and make it evolve using this dynamical equation, namely the Klein-Gordon equation and also the Einstein equation, and this will be a completely coupled evolution. And at the end of it, whatever remains, and we look at it and examine its properties and see what kind of space-time it gives rise to. This kind of problem, the particular problem that Chopwick explored, had a one-parameter family of data labeled by this parameter P, which, roughly speaking, signifies with what strength the scalar field interacts with the gravitational field, and this can be taken as some sort of coupling. Or for example, in some particular scenario, this P can be taken as the amplitude of the Gaussian if the scalar field had an initial Gaussian profile. What Chopwick observed in his numerical investigations was very interesting. He saw that below a certain critical value P star for this parameter P, after the scalar field has evolved and dissipated, whatever remains is just flat space, empty flat space with no interesting structure behind it. But as he kept cranking up this parameter P, above this certain value P star, he found that the final space-time, after having evolved the data, is not just empty flat space, it has a black hole in it. So this is the mass of the black hole, and more interestingly, around this critical value P star, the mass of, the mass of the black hole follows a scaling law. So the minimum mass of the black hole is a zero mass black hole, which happens exactly at the critical value P equals P star. But away from it, there's scaling law plus P minus P star to the alpha. And this is known as Chopwick scaling. Note that this P and P star, etc., they are completely non-universal. This depends on the particular kind of matter field under consideration and various other tunable properties of the scalar field. So this is largely universal. This itself by itself has very little physical significance. However, no matter what the kind of scalar field he took, no matter uh, uh, whatever other parameters he adjusted, he always found this particular scaling law with this exponent, and this shows some sort of universality in some given theory. And this is the field that this is the discovery, pardon my misstatement, that gave rise to the field of criticality in gravitation, and it's by now a rather huge field with many investigations taking place since Chomsky discovered this very curious phenomenon. Yes, please.
So, what do you mean by universal in a given theory? I mean,
In a given theory, the meaning, for example, if you have Einstein Maxwell, then this alpha might vary.
not only scalar.
No, no. So initially, the initial investigation that only had Einstein gravity plus scalar.
Yes.
But you can have some other theory. For example, you can add some other dynamical fields and some other
So,
coupling.
do you mean field content or do you mean the potential?
The potential and the couplings. The,
How is it universal?
no, universal in a given theory in the sense that if you have some, let's say, basic theory, I'll try to explain what I mean by universal later. Uh, it also depends on the field content. It's universal in the sense that no matter what your initial profile of the scalar is, no matter what you try to do, it will show this sort of scaling behavior regardless. And you can add various fields to your theory, but then that would be changing the theory in some sense. And for example, if you can have charged fields.
No, I'm asking
Yeah.
what is universality? What?
Yeah, it's universality with respect to the initial data. The family of initial data are very wide family of initial data. Actually, all kinds of family of initial data. So okay, it's universal with respect to initial data, but not universal with respect to the field content. It's in that sense universal.
P star is not universal. The same.
Yeah. P star is non-universal even in a so P star it depends on the family of initial data. Different members in the family of initial data might have different value of P star. And please, this goes without saying that at any point, please interrupt me and ask me questions. I'm not even sure I'd be able to finish the talk, and I don't really care about that, but I need to convey something, and that's more important to me than just finishing my talk. So thanks for the question. And there are several other important features in this problem. Around criticality, namely around this value p equals p star, the space-time becomes sort of self-similar, and this self-similarity can be of discrete nature or of continuous nature. Continuous self-similarity is what I'm going to talk about today, and continuous self-similarity is often characterized by the existence of something called a homothetic killing vector field, which is defined by this following relation. Namely, if xi is a vector field, then the Lie derivative of the metric with respect to this vector field is just a multiple of the metric itself. And for convenience, the factor is chosen to be 2. Note that this is different from the usual killing vector field. This does not generate an isometry, because in the usual killing vector field, when it's an isometry, then the right hand side here is 0 instead of a multiple of the metric itself. This is a very restricted class of a conformal killing vector field for those who know this term. And when we assume the existence of such a homothetic killing vector, the analysis becomes really tractable. And you can write down the whole system of equations in terms of just one variable, which is related to this Killing vector field. And this whole system of coupled equations, including the Einstein equation and the other matter equation, this can be cast as a dynamical system. Which brings me to my next point, that we can have a very nice dynamical systems picture in describing the dynamics of the gravitational field and the scalar field. And in this sense, the physics is rather easy to understand. So this line here, this is a one parameter family of initial data, and this I hope clarifies some of the points that I was mentioning earlier. So this is a space base of solution, and each integral curve represents a different space time which evolves from some initial data which is characterized by this line. And this way of casting the equations of motion shows us that there are two basins of attraction in a problem in the phase space. One is a black hole fixed point and another is a flat space fixed point. And as you keep varying, you find that there's a critical point here which has one unstable direction, which is basically a saddle point in the language of ordinary differential equations. And if you start with some small value of this one parameter family of initial data, one flows to some flat space fixed point. This is one basin of attraction. And if you make it large enough, one quickly flows to the black hole fixed point. The hardest part of the phase space to explore is this critical point, for which your initial data has to be extremely finely tuned, and which also presents a problem for numerics, because this sort of fine tuning is difficult to explore. And it's this critical point, it later turned out, that governs the scaling exponent, which is associated with Chopwick scaling.
What are the different directions?
So this so this is actually some infinite dimensional gravitational phase space. There can be infinitely many parameters, and each of the curve is a particular space time. So each integral curve in this phase space corresponds to some space time, and this flow is generated by the homothetic Killing vector field Z. Okay.
But all these space times admit the homothetic field.
No, yeah. So it's an assumption. Not all admit homothetic Killing vector. So sometimes the homothetic Killing vector, the existence of the homothetic Killing vector is an assumption, as in the case that I will be describing, because it simplifies the analysis and it enables us to make some very concrete analytical statements about these spacetimes in question. In general, for example, when Chopwick first did his numerical investigation, there was no such analytical description available. In fact, for example, when the self-similarity is discrete in nature, there's no homothetic field available, and then it's much more difficult to explore this analytically.
But can you have the last line says here? I'm just getting
Sure.
ahead of you.
Sure, sure.
So this last line says you can have ADS like asymptotic. How is it possible to have homothetic field?
Yeah, that's a great question. I said ADS like asymptotics. It's not ADS, and that's indeed. For example, homothetic Killing vector is incompatible with a positive cosmological constant. So it has ADS like asymptotics, but the cosmological constant that's due to a scalar. This has asymptotic like ADS, but the curvature at the sort of in the asymptotic region that vanishes, and that can happen because of some very special kind of scalars and some very specific parameters that are present.
Okay, let's see.
Yeah, sure. So let me now describe the motivation for this work. So it turns out that choptic scaling and all the related phenomena that are observed, people usually assume some sort of spherical symmetry. So the essential dynamics takes place in two dimensions, one being the radial direction and the other is the temporal direction. The other directions just come along for the ride, and they in the from the two-dimensional point of view, they're just some additional fields. So studying this sort of gravity in two space-time dimensions and then uplifting it can describe a wide class of scenarios. For example, I will also have a gauge field, and if you consider this gauge field from the point of view of Kaluza-Klein reduction, this could be uplifted to rotating black holes as well. So this is one of the motivation that uh, initiating the study in two dimensions could help shed more light on high dimensional space-time, where uh, sometimes the direct application or direct solution of the equations of motion are more difficult. And more importantly, at least for me, two-dimensional gravity is a playground for serious quantum gravity questions, and it has become more so in recent years. For example, many people have tried to address questions related to the famous information paradox based on some two-dimensional toy models, and people have made substantial progress in it. And also in two-dimensional quantum gravity, matrix model and string theory are important tools with which we can address important non-perturbative questions about gravity. And this question is certainly one that I eventually wish to address using this tool. And as I'll say later, some of these solutions have areas like asymptotics. And in this room, there are several people who have contributed to the study of holographic correspondence and various aspects of the ADS-CFT correspondence. And if this turns out that this work leads to some understanding of holographic correspondence in some low-dimensional models, this will be certainly a worthwhile effort. So let me describe without further ado the two-dimensional model. I'll begin with a very general model of the two-dimensional curvature coupled to some dilaton field phi, and this Ricci scalar is coupled to this phi in this very specific way, where for now this potential function a phi is unknown. There's also this dilaton kinetic term. It turns out that in two dimension, one can get rid of this dilaton kinetic term by a Weyl transformation, but I choose not to do that because one of my motivations in studying this question is relating it in a straightforward way to higher dimensional space times, and sometimes Weyl transformations may obscure some of the properties of singularity. So I'll keep this kinetic term for now on. And in a very general manner, I have added this potential function for the dilaton. And since my motivation is also to study higher dimensional rotation or even higher dimensional gauge theories, I have added a Maxwell term coupled to the dilaton term. So this is some very general model to study. And it will turn out that just the assumption of self-similarity is sufficient to restrict the form of this potential quite severely. And we'll see how that takes place. So my first goal is to determine the form of the function a phi that couples to the Ricci scalar in two dimensions. So we will work with two equations of motion which come from varying this action. This first equation of motion comes from varying the dilaton field phi, and the second equation of motion, this comes from varying the action with respect to the metric and then taking its trace. So these are two scalar components of the equation. A crucial fact in our analysis is that the Ricci scalar transforms under the action of homothety by the following relation. It's just a multiple of itself with the constant -2, and it's for this reason that Professor Lahiri mentioned that a constant cosmological constant space-time is incompatible with homotheity. But our attention is not only on the Ricci scalar. We would also need the transformation property under this homotheity vector of the scalar field phi. And one can make a very general assumption that the scalar field under the homotheity action transforms only to a function of itself, which I'm calling f phi. So what will I do now? What I'll do is I'll apply the homotheity transformation property to these two equations and demand that the equations of motion transform to themselves, because in the end what I want is a self-similar space-time, and if the solution to the equation of motion does not respect the homotheity symmetry, then we are not doing something right and we won't have what we want. So the transformation laws, when I apply it to the first of these two equations, we find these two relations. That this function f phi is related to the dilaton function a phi by this two relation. In one case, f phi is just a prime phi over f phi with some constant a1, and in another case, f prime phi is just 1 over a phi. Just with these two equations, it's not possible to solve for both the functions simultaneously. So we would need some additional data. And for that, we would need to appeal to the other equation of motion, namely the second equation of motion I flashed at the end of the slide of this slide, this equation. And this equation of motion yields this relation. And these equations are then sufficient to determine the functional form of A. And it turns out to be rather simple, although it's a nonlinear equation. The solution turns out to be quite simple. It's simply sine hyperbolic square function, and it just follows from this, from the two of these three equations that I derived. And it also turns out that the other equation that I mentioned as a relation between f and a is also satisfied by this form of the function. However, as far as dilaton potentials or dilaton coupling to Ricci scalars go, this form of the function is quite hard to work with, or at least I found it very hard to work with. And to make further progress, I will take two special limits of this function, and it turns out that they are quite well known in the literature. The first of these models, which I will refer to as the stringy model, is a particularly simple case where this function a phi is just e to the -2 phi. Again, this I chose as a sort of adherence to convention, and I could have chosen any constant, but then I sort of traded this choice for keeping this coupling gamma undetermined, which actually makes sort of the connection to higher dimensional physics more transparent. And this form of potential is related to two-dimensional target space string theory. So string theory is, of course, as you know, the Walsh theory of string theory is two-dimensional, and critical string theory or critical superstring theory, for example, lives in 10 space-time dimensions, and you can compactify various dimensions and get some lower dimensional physics. And in this case, the target space itself, as in the space-time in which the fields live, is two-dimensional itself. And for string theory, the coupling gamma that I had flashed a few slides ago, that has the value 4. However, for some physical reasons which I explain in my paper, we have to have some upper case.
So can you give this thingy model as the special case of your general formula?
Yeah, yeah. In actually, it turns out that in these equations, uh, if you it's one of the limits, you have to take one of the constants to 0. But if you take that constant to 0, this potential vanishes.
Right.
But if you see, you will find that okay, if you go back to the original differential equations, that e to the minus 2 pi or any exponential function is admitted as a solution, and everything else is consistent. So it is one exact solution of the homothetic equations.
So it's kind of a singular solution.
Yeah, it's a very singular limit of this function, but otherwise it's quite general. And I'll come to another solution which arises directly as a limit of a particular solution, which is the Liouville model. So once I choose this form of A phi, the homothetic transformation property of phi turns out to be very simple. Namely, the function f phi that turns out to be a constant. And in the literature, this constant is typically referred to as minus kappa. So I'm calling this minus kappa. And once you determine this, everything else falls into place. The potential function is determined. The potential function is a sort of separate function which appears other than the Ricci scalar in the original action. That is determined to be of this form, V naught e to the 2 phi over kappa. And moreover, the gauge coupling itself, whatever is in front of the Maxwell term, that is also determined unambiguously in terms of kappa. And as I was mentioning, there's another model which arises quite naturally by taking the limit. And this is quite easy to see. If you take, I think, let's say this A3 to 0 limit, then it becomes a quadratic function. This Fi becomes a quadratic function. And this is the quadratic function that you get by taking this particular limit. And then you realize quickly that you can make a field redefinition to make it come to some other well-known form, which is nothing but Liouville model, in which the scalars sigma. So this sigma and sigma, I've just made some artificial splitting, because this sigma naught is a topological term which contributes to the ground state entropy in 2D black holes. And we have this very simple form, and again we can apply the homothetic transformations to determine V and this gauge coupling function G, and these are again determined in terms of this kappa quite easily. There's some enormous simplification happening on account of the homothetic symmetry combined with the Maxwell field. In both the models, we can have some non-zero electric charge Q. This is just some point charge. And in the absence of any other additional charge fields, it turns out that the sole effect of the gauge field is to additively renormalize the potential strength. For example, if you just put this gauge field on shell here with this charge Q, what it will do is simply shift the value of this potential of the potential strength V0 by the charge. So in studying the effective dynamics where we have no other additional charge fields, we can simply forget about the gauge field altogether and simply work with the dilatonal gravity system. And this is another simplification of the analysis, which is thankfully accorded to us by the homothetic symmetry. Okay, now that I've derived the potentials and everything, is there any questions that need addressing at this point? If not, then let us go ahead and let me discuss static solutions. So now that I have determined the form of the potential, which is consistent with homothetic symmetry, and note that this is at this point there are really 0 degrees of freedom, because there are no dynamics so far in whatever I've done, because even in 2-dimensional gravity coupled with scalar, even with gauge field, that remains non-dynamical. So at first, but even though it's non-dynamical, it admits black holes. But I would like to know now is what sort of static solutions this model has, so that it allows us to build more intuition about the particular system. And for this, I can put the metric in some Schwarzschild-like gauge with some time-independent dilaton phi. And for the stringy models, just by solving the equations of motion, we can find this sort of solutions for the dilaton field. And for the Liouville model, the sigma, that's again some sort of log R value behavior for the dilaton field. And having put this in Schwarzschild gauge, we can solve for this function fr, and we get this rather complicated form. And this has a black hole horizon at r equals rh. Okay, I don't remember if I put it in the previous slide, but let me say it anyway. That these black hole solutions are not self-similar in general, because they have some intrinsic scale. It's just a solution to the equation of motion or from an action which is consistent with self-similarity. That does not mean that the solutions will always have self-similarity, and this is something that I needed to emphasize. And for sensible space-times, we have to have this effective potential strength to be positive, and this self-similarity parameter has to be greater than some value which is this gamma dependent. And this sort of constraint is useful in this sort of numerics in studying singularity dynamics. But this is the more important aspect of the problem that Professor Lahiri was asking. For this sort of space-times, the asymptotic causal, we have some black holes, but the asymptotic causal structure, that is crucially dependent on this value of kappa in relation to the coupling gamma. If the value of kappa is large enough, you can try to study the fall off of various fields, and if you try to construct the Penrose diagram, you will find that instead of a sort of null boundary as in Minkowski spacetimes, you find yourself, you land yourself with some time-like boundary as in ADS spacetimes. And this is what is known in the literature as some unusual asymptotics space-time, where the causal structure is ADS-like, but the curvature still decays to 0 at asymptotic infinity. And this is possible only when there are some exotic fields or dilaton fields present, and where the dilatons run in some particular way to make this happen. However, for gamma, sorry, not however, for some particular limits, for example, when gamma equals 0 and when kappa is very large, this almost approximates ADS to space-time, and this is very similar to the Jacob-Teitelbaum model, which has been the focus of many recent investigations in solving the 2-dimensional path integral of quantum gravity and understanding information paradox and so on. The other system is Liouville system, for which the Schwarzschild blackening factor is of this form, and in this case we can find some similar constraint for fields. Yeah, no, Schwarzschild gauge meaning this form. Yeah. And in the case of the Liouville system, the asymptotic causal structure is always ADS-like, and the curvature always decays to 0. and it becomes some purely ADS like in the limit of some infinite limit of kappa, negative infinite limit of kappa. So these are all I had to say about these static solutions. Are there any questions at this point?
Are there horizons?
Yeah. There are horizons. So
all
for
of these kappa?
Hmm?
For all kappa?
yeah, there are horizons. So for this particular solutions, when at r equals rh, the FR is 0.
Right.
And this is why I try to write it in this manifest form where the horizon is visible, because whenever you put r equals rh, it becomes 0. For all kappa which satisfy these constraints, there is a horizon.
But
Yeah.
when kappa is large, there's not going to be.
Yeah. But when kappa, then it's going to be some very singular space time, and then it's going to be another hard to interpret.
Okay.
Is it okay? Great. So now that I have discussed static solutions, let me discuss self-similar solutions. So in higher dimensions, when people study self-similarity, people typically start with some coordinate system like the advanced Bondi gauge, where the metric is of this form, where R and V, so this is sort of the Eddington-Finkelstein like coordinate or the advanced time coordinate. And you will see that immediately that this metric, when you transform it to R, goes to lambda R and V goes to lambda V, the line element goes to lambda square of the previous value, which says that this R del R plus V del V, this vector is a homothetic killing vector for this metric answer. So now we want to study this in two space-time dimensions. So we obviously want to discard this additional spherical directions and just work with these functions. However, there seems to be some sort of an overkill because the G bar appears as an overall conformal factor, and it turns out that not by a conformal transformation, but by actually a diffeomorphism, we can, by a series of coordinate transformations, we can reduce this to a very simple metric ansatz, which is the Eddington-Finkelstein like gauge, where this fx plus 2x appears as a coefficient of dv square with x as rho over v. Remember, this rho that I have written here is different from the radial coordinate with which I described the static solutions in the previous slide. And it's in terms of this coordinate x with which we can write down the ordinary differential equations, and this is the self-similar independent variable. So now, having put the metric into this useful gauge, we want to write down the vacuum self-similar solutions. Because of the self-similarity, the scalar field, I'm now writing explicitly rho v, this can be written as this very simple form with one function capital phi, which is a function of one variable rho over v, minus kappa log v. And quite a similar expression for the function sigma, where we will have this capital sigma instead of this capital phi. And for the string system, we will write down the solution after we can write down this following solution, and this solution for capital phi will have the following form. However, if you have paid attention to the previous slides, this will perhaps look very familiar to you, and that is not an accident. So let me just show what why it should look familiar. Note this form of the function f and phi, and note this function without this term, And note this form of the dilaton, the static dilaton. So this similarity motivates us to think that they are not actually different solutions, but they're the same solution in disguise in a different coordinate system. So this is the zero mass static solution. So this is the case where there is no horizon, just a singularity, where there's no scale anymore. And the zero mass static solution in the Eddington-Finkelstein coordinate system reads like this. But by an explicit coordinate transformation, with the coordinate transformation given here, we can bring it to exactly the form that I had shown in the previous slide. So this is not at all surprising, because we are studying simply the vacuum sector of 2D dilaton gravity coupled to gauge field, where there is always some static solution, where every solution can be put in some static gauge. And this is not at all surprising that this happens. What is surprising is that something non-trivial and static gets back to something non-trivial and self-similar, which is a specialty of two-dimensional gravity and which does not happen in higher dimensional space. And there's a very similar story for the Liouville system, and for also for the stringy system with the coupling gamma equals 4. And if you are interested in the causal structure, this is what it looks like. When the asymptotics are Minkowski-like, then there are some null singularities present, and there could also be some time-like singularities depending on the value of kappa. And these time-like singularities are in tension with the weak cosmic censorship conjecture, and we'll see that although they are not good starting points, this sort of singularities would be unstable whenever there is some non-trivial dynamics. And when there are asymptotic causal structure like ADA space-times, then there are null singularities present in the space-time. And this sort of causal structure is at least consistent with our expectation from a self-similar space-time. Because if there were, for example, some horizon present, like in the static solutions, that would imply the presence of a scale in the problem. And this scale is obviously in tension with the assumption of self-similarity, because self-similarity says that no matter which scale you go to, the spacetime will always look similar. But in this case, obviously, that's not true. Where the black hole horizon radius gives rise to some explicit scale in the problem, which is inconsistent with self-similarity. So so far, it turns out that the self-similar vacuum solutions are somewhat of a triviality. So in order to go past the triviality, we have to add genuine degrees of freedom to study dynamics, because so far the system is completely non-dynamical. There is no dynamics. So we should add some additional matter, but since we want self-similarity, this additional matter field also has to adhere to the constraints of self-similarity. So let me consider the simplest possible thing to add at first, which is a scalar field psi, with where very similar homocity transformation as before, where the Lie derivative of this additional scalar psi is some minus lambda. Constant. That's simple to study. But it turns out it comes with a catch in the stringy system, because the scalar couples to the Ricci scalar couples to the dilaton in this way, this scalar field cannot be minimally coupled. So one has to have some dilaton coupling to make this work. So inside the bracket it looks minimally coupled, but it's not, because there's this dilaton factor sitting outside. And although from the point of view of 2D, this might look contrived, this sort of coupling to dilaton, non-minimal coupling to dilaton looks contrived. But this is what naturally arises when you consider Kaluza-Klein reduction of some higher dimensional scalar. If you consider this scalar in higher dimensional space-time, and if you Kaluza-Klein reduce it, then this factor will naturally arise because of the volume modulus associated with the higher dimensional volume element. So from the point of view of higher dimension, this is natural, and in fact, this could be uplifted to various other scenarios. And now we can write down the dynamical equations. And there are a lot of gauge redundancies in the equations of motion. And it turns out that all the dynamics of the matter gravity system can be determined by two second order ordinary differential equations involving just this dilaton field and the matter field. And that will determine all the properties of the space-time. And this capital psi is nothing but the self-similar part of this little psi, where there is an additional part like log v as before. The first of these two ordinary differential equations is actually quite reasonably simple. It's a
Capital psi is small psi plus.
yeah. I think for reference, I better write it down. So small psi, which appears in the Lagrangian, that's capital psi x.
Psi or phi?
Oh, sorry, phi minus kappa log v, and likewise for psi. And for this is lambda. Thank you.
And kappa is still less than -2, right?
Yeah, so right now there's no constraint that we need to impose, but we'll keep imposing this constraint. But as far as the equations of motion are concerned, this is always a solution. From the equation, if you consider just the equations of motion, then there's no constraint that you need to worry about for the moment. So the first equation here is of this form. But the second equation is not as beautiful or as compact as this one, and this has this very ugly form. But ugly as it is, we can make a few statements about it. Whenever we have some differential equations like that, we can decouple any second order equation into a pair of first order equations. So we can have 4 first order ODEs where we can write the equations in this form. And we, because we need to study the critical point, which is a fixed point of the differential equations, the fixed points must have this property where this sort of momentum variables should both be 0. However, it turns out that if you try to solve for the Jacobian matrix, which arises out of this 4 first order equations, the eigenvalues of this Jacobian matrix are all 0, and we cannot say anything about the stability of the fixed points. In fact, it will turn out that the naive method of linearization itself becomes inapplicable because of some singularity in the equations of motion. So we have hit some sort of a roadblock, but let us proceed anyway, and we'll see that it is this problem that will be able to turn it into a strength. So we will also consider the Liouville model, and we can add matter to it. And for the Liouville model, because the Ricci scale, it's only the Ricci scalar that couples linearly to the field sigma, and the rest are sort of completely decoupled from the Ricci scalar or doesn't couple the same way. We can add minimally coupled matter here easily. And in this case too, we will find that there are some very similar issues with linearization. In this case, it turns out that we can think of some questions related to quantum gravity. For example, you can study the quantum back reaction of matter fields in a certain semi-classical approximation. If you add some n number of minimally coupled scalar fields to the pure gravity sector, then in the large n limit where n goes to infinity, but where this g is small, where n times g is some finite number, this is some sort of soft limit in case of gravity. The conformal anomaly in this case can be reproduced by a single non-minimally coupled scalar chi, where this factor n sits as an overall factor outside the matter action, and which couples to the Ricci scalar. And if you consider this system with this pure gravity system, you will find that this also is consistent with the assumptions of self-similarity, and we can derive some similar equations as before. So this will help us study or at least address some semi-classical quantum gravity questions. Okay, any questions regarding this section? So how much time do I have? 10 minutes. 10 minutes. Okay. So I'll describe this section in detail. I'll probably not go into the details of the numerics, but I think this will be a nice place to stop afterwards. So let me describe now a toy model, which is quite relevant in the particular systems that I was studying. I'm sorry if it's not visible here, but I can probably draw it here. Is there a duster? So I said something about turning the difficulties posed by the inapplicability of linear stability analysis into our strength. And for this, we will study at first simply this dynamical system x dot equals x square. And since it's not clearly visible on screen, let me write it down on the board. This dynamical system, at this point, forget anything I have said about the gravity so far, the gravitational system so far. This dynamical system has a fixed point at x equals 0. However, if you try to linearize it, of course, you can't say anything about it because the eigenvalue itself is 0. But we can see from the phase diagram that this fixed point is half stable. There's one stable direction and one unstable direction. So this is the unstable direction and this is the stable direction. Quite importantly, this dynamical system shows the phenomenon of finite time blow-up. Namely, this equation has this solution with this initial condition. When x0 is epsilon, this xt blows up at t equals 1 over epsilon. This blow up can occur in the future or it would have occurred in the past. And this is quite well known in the theory of nonlinear differential equations by the name of finite time blow up. Quite interestingly, this finite time blow up that is quite helpful in teaching us something about the singularity in the gravitational system. Why so? In this slide, I'll write down the equation here. Okay, something positive. If we identify this dynamical variable phi prime x with x, and let us forget about the matter field here, then the equation of motion satisfied by phi prime is completely similar to the equation, the toy model equation that I wrote down here. X dot equals x square. If you take phi prime to be x and make a redefinition of the time coordinate, you will land with exactly the same equation. And precisely at the instant, or rather, sorry, this is not the instant, this is let's say if you write the equation in time domain, if you plot it in time domain, you will find that at a certain time this blows up, and precisely at the instant that the finite time blow up happens can be mapped to the singularity of the system. Namely, the space-time singularity that we see in the two-dimensional model is associated with the blow up of the uh, dynamical of this phi field or phi prime field, and this gives us a nice handle on checking for the dynamics of singularity in this differential equations.
It's an unstable bit.
It's this one, yeah. This one is, yeah. Generically, it's an unstable fixed point.
So
So
if you have closed bit, it will go to infinity.
yeah, or it can even have if you consider the time reversal. I mean, there's some issue with time reversal. I mean, in this particular case, there's I won't have the time to go into the detail, but there's no natural notion of the time variable here. So the infinite is, or rather the asymptotic region is where you impose the boundary condition, and it will sort of flow to a region where there's a singularity, and there's always one trivial solution which is staying at this fixed point. Always the space-time is always flat. It's just the trivial solution. But even if you perturb very slightly away from this fixed point, it will blow up either in the past or in the future, depending on what convention you choose for your self-similar variable. But the point that I want to make now is that even in systems which admit linear fixed points, finite time blow up is quite generic. For example, again, this is not clearly visible. Where did I put the chart? If you consider some dynamical system like this, then although you will have linear fixed points. So this and this are linear fixed points because you can obviously draw tangents through here, and these tangents are non-zero. It will turn out that if you start with some initial condition over here, you will see some finite time blow up, which goes to show that finite time blow up is not always necessarily associated with existence of linearization, and which is rather generic in dynamical systems. So I'm sorry, I erased that equation. To model the effect of matter, we can add some additional square piece in this dynamical equation, and which was exemplified by the psi prime square term in the equation of motion. Sorry, I should just go to the slide. This psi prime square term in this equation, this can be modeled by this equation, where instead of a 0, we simply have some parabola which is displaced from the origin. And in this case, obviously, we would also continue to have finite time blow up, and the singularity is found more quickly than before. So earlier, if the singularity was formed at a time t star equals 1 over epsilon, now the time scale is reduced, and by this factor 1 minus delta square over 3 epsilon square, which shows that if you have singularity present in the geometry, in the static geometry to begin with, even if you add matter, it won't get rid of the singularity. In fact, it will bring the singularity closer. Your singularity will become more unstable in some sense. And if your test particle had a lifetime of, let's say, 1 over epsilon, and it will, in the first place, now your test particle will have a shorter lifespan. This shows us how the singularity structure manifests itself through these equations of motion themselves by some very well-known fact about ordinary differential equations. Now I think I have almost run out of time, but I'll say only a few words about the dynamical system. And this is actually the bulk of the work, which I don't have the time to go into. And there are lots of boundary conditions that you need to be very careful about when you are considering the matter dynamics coupled to gravity. And so just very briefly, I have considered here the nature of singularity, and you can also see, for example, the formation of apparent horizon in the space-time whenever there's a space-like singularity. And you can check for some Choptic-like scaling law by looking at the quasi-local mass. Remember that since we are considering a very dynamical situation here, the ADM mass is sort of a very delicate concept to apply here. So the quasi-local mass, that's of a more immediate interest here. And these are some numerical plots. So again, some part of the diagrams are not visible here, but let me just describe it. So here what I do is at a certain point in the advanced or null coordinate, I turn on some scalar pulse. Before that, we have some vacuum system, and after a certain point, I turn on matter dynamics and see the resulting features in numerics to deduce the nature of the singularity and so on. And there are various sorts of singularities that I found. Sometimes there are space-like singularities being formed out of null. Then sometimes the singularities remain null, but they have effectively moved out of their original positions. And when, although even the initial system is sort of sick in some sense because of a time-like singularity, it turns out that such time-like singularities, if you start with them, they are unstable, and the system quickly settles into some space-like singularity, and so on. And at the end, I would like to say that even in this case, there's some topic-like scaling that I found. So this mass here, which is analogous to what Stokely did, is nothing but the mass of the quasi-local mass on the apparent horizon. And this lambda is the parameter which I'm varying from some value, and which is the which plays the role of the critical parameter in my scenario. And it turns out that if, as I keep varying lambda and I make a log-log plot, there are two piecewise linear slopes which fit the data quite beautifully, which says that there are some sort of two critical scaling laws which are present in the particular system. And I was able to determine these critical exponents numerically. One is 0.8 and the other turns out to be 1.9. And I have a possible analytic explanation for the exponent b, and although I have to look into it with sort of more detail, and this analytic exponent comes from just the quasi-local mass at asymptotic infinity, which shows the lambda square behavior. And it turns out that this beta with its value 1.9 is quite close to 2. So it might well be that this second exponent is actually exactly 2, and it might be because of some numerical artifact that this comes close to 1.9. And let me just flash a few future directions, and I won't read them aloud now. And there are many things to do, and this is sort of the first in a series of papers that I have written, and I want to come back to many of the points that I have not explored in this paper in the future. And thank you for your attention, and I would be happy to answer any other questions you have.
Thank you. Nice talk. So time for questions now.
So this is your first paper on unit.
Not necessarily. Not first.
You said this is your first in a series or something.
Oh yeah, no, first in a series of this exploration. So I want to explore more.
But not the first numerical therapy.
Yeah. First in numerical gravity, yes. Yeah. Actually, I've done lots of numerics even during my undergraduate days, and also during my PhD, I did something on with numerics, trying to understand gravity, but that remains unpublished. Maybe someday. So yeah, this is the first publicly available paper on numerics that I have written. Please.
What do you mean with homophoby?
Oh, homotheity is that's a concept in mathematics which relates to some sort of scaling transformation. That's just a name as far as this word is concerned.
You consider here homophoby symmetry.
Yeah.
So what is the importance of this?
Yeah. So that's a good question. So it's sort of phenomenological or numerical observation that the space times that show this critical behavior, they are often self-similar, and sometimes when they are self-similar, they admit this homothetic killing vector, and whenever there's a homothetic killing vector, this simplifies the analysis, and that's the reason.
So not consider this symmetry.
Yeah.
So calculation will be some.
Yeah, and calculate. I mean, I'm not even sure there would be how feasible it would be to make analytic calculations, because whenever there are discrete self similarity, people have to do some sort of numerics, and people see these echoes in numerical experiments.
But then the feature that you have obtained by assuming that you have a homothetic killing vector,
Yeah.
if you relax that assumption,
Yeah.
then are those features going to persist? The observations that you have made now.
Yeah, I think they will in some sense be even richer because this is obviously much more restricted and this I think will restrict the dynamics. But if you keep relaxing some assumptions, then you will get something more exotic for sure. Please.
You said that when the kappa will be infinitely.
Yes.
Exactly. Yes. So
Yeah.
does it mean that having kappa, if we have kappa, will just shift from one space time to another kind of space?
Yeah. So it's a parameter in the Lagrangian. It's a parameter in the potential. I mean, it's a very different space time. You are changing the coupling. So obviously that's
a one parameter family of space.
Exactly.
But one thing you want to mention that you can generalize this to higher dimensions.
Yeah. I mean,
but the things that you have talked about here are all restricted to 2 dimensions.
Yeah, all restricted to 2 dimensions. So in higher dimensions, you have to make the translation as to the what the field phi corresponds to, and there you have to have some mapping, and there you have to translate the dynamics. So right now I'm considering 2 dimensions because even in itself 2 dimensions is quite interesting to me and quite interesting to study because of the various developments in recent years. But if we want to know more about our world, so to say, then at least this could be some starting point in generalizing it to higher dimensions.
Other question? Other questions from the online people? Only Punoda is there.
No, I don't have any question.
Yeah. So I also observed that you got this asymptotically ADS kind of thing, ADS2 kind of thing. But then your curvature is on the ADS boundary, the curvature vanishes.
Yeah. On ADS like, so that's why I always appended the word like to it. It was to be careful. Yeah, it's quite simple actually. Okay, let me just go. It's in my paper. So, for example, from the Liouville perspective, it's quite easy to see. Yeah. So this FR is what appears, in the metric in the Schwarzschild-like line element, And if you take this kappa to be very large, this becomes simply R square.
Large, you mean positive large?
Negative,
Or
large
negative
negative large.
Okay.
So this factor vanishes and this almost becomes R square. And inside it, it's just RH over R. So essentially this remains R square. And if you, and in ADS, any,
So
yeah.
this first term is like R square.
Yes.
And this
Second term is 1 over R. So it's R square minus R. It's
R square minus 1 by R square minus R.
R square minus R. So you can always write it as a square in R. And any square in R, you can write it as some ADS kind of metric. But the curvature, so when it's exactly R square minus R, the curvature is constant. It's this curvature is -2. But I mean, there's an order of limits that you have to be careful about.
So that is exactly ADS.
That's exactly when you take the kappa to. So if you start with, for example, even within the action and take kappa to infinite limit, and it's actually more obvious in the stringy model. The action simply becomes the following form: e to the -2 pi r plus 2, I mean, in some units. And when you vary this with respect to pi, this gives you the equation of motion r equals -2, and this is nothing but the JT model. Actually, most of my PhD was on JT model itself, and this gives you some constant scalar curvature. But again, as I say, you have to be careful with your order of limit, I mean, which you take to infinity first, r to infinity or kappa to infinity. And so if your kappa is fixed, and I mean, it's at least plausible from this way of saying that once, if you have large kappa, and if you look at the region which is near the asymptotic, it almost goes as r square. So this is a limiting scenario in which the equivalence with ADS to space-time is clearly visible.
Any question? If not, let's end the speaker once again.
Thank you all for being here.